All right, I'm going to cover a few things today. I really want to talk about Dyson Spheres, and you're going to learn why that has something to do with AI for good partway through the presentation. We'll get there. Okay? Oh. Lit. All right, so I'll give you a little bit of background on myself to begin with. I'll talk to you a little bit about Strong Compute, which is the company that I'm running now. And then we're going to have a look at the research that people are doing on Strong Compute. And there's opportunities for you to do research on the platform as well. We're giving out grants, running some hackathons. Oh, right, mic up. And then we're going to talk about the Dyson Sphere, where that fits into everything. All right, let's kick it off. So I grew up building computers, built about 1,000 computers. And then I found out what startups were and came out to Silicon Valley. I was building games to teach AI development, neural nets, things. I co-founded a company called Meta, which builds augmented reality glasses. It's probably different to another company you put up like that. In 2013, I was the Y Combinator, and I was the first person to open the door for Zuckerberg when he came in to talk to us. He said, "Hey, I'm Mark, I work at Facebook." And I said, "I'm Ben, I work at Meta, we make augmented reality hardware." And I went, interesting. So, yeah, I might not tell him about this one. And then I went and coached a bunch of companies. I had a really cool hackathon where we did built some self-driving cars, like Mad Max style in the Australian outback. Spent a bit of time with Offer Family, and then got started on Strong Compute. So, what is Strong Compute? Oh, sorry, before we get there, this is the things that I care about. All right, I like the really far out there stuff. I got a whole presentation on being RoboCop, living forever that way. I want to build Dyson Spheres. I want to figure out what's going on in here and in all of your brains as well. So that's what keeps me up at night. All right, so Strong Compute, right? We want you to feel like all the compute in the world is just connected to your laptop, right? You don't think about clouds and how everything's working anymore, all right? So just think like what the scheduler does for your CPU, but imagine that was running at the scale of the world, where every cluster is a core, the jobs are all getting run around everywhere. You just write once, run anywhere. We like things to go extremely fast, right? We've got some really good speed numbers on AWS, actually. I think we've got some people here from AWS. Yes? All right. We've set all our speed records on AWS. Would love to share that at reInvent. All right. Okay, so, clicking? All right, so we don't want you to do any more ops, all right? If you're in AI, you don't do ops anymore. You just experiment. You have one container, runs absolutely anywhere you want. You don't change a thing. You say, I want this many GPUs, and it goes. Goes really fast. So on Amazon, we can move data on the cluster at 90 gigabytes a second. We can move data to the cluster at 60 gigabytes a second. And we can move data to a single instance at 20 gigabytes a second, which means we have the world's fastest container registry. So you can take a 70 gigabyte container and you can actually pull it onto the machine and start it inside of 10 seconds. So yeah, got a whole lot of stuff that we could show there. All right, someone's going to need to hold this up for me. Okay, for all the people paying for the compute, they don't like it when the bills go crazy. So we fixed that. You can see how much money you're spending, you can cap it, you can do whatever you like. For the people controlling the compute, you can just see where all the jobs are actually running. You don't manage it with Slack and phone calls anymore. You can visualize all your compute jobs the entire world over and move them wherever you'd like them to go to. Cool. All right, and this capability, a lot of it is live today, and we'll be having a big launch very soon where all of this comes to pass. Okay, so what are people doing with our compute? All right, we've got this really, really cool one. This is Cortical Labs. They've decided that maybe the future of compute isn't GPUs. Maybe the neural matter that we've got is where it's really at. But you want to be able to program it, right? So what they're doing is they're getting neural tissue and they're putting it on a petri dish, and then they're sticking a chip into it and trying to train the neural tissue. They've actually got it playing Pong It's human neural tissue. And I asked Hon, what happens if it becomes, sentient? When would it become sentient? He said, I'm not quite sure. I was a little concerned about that answer. But, maybe he doesn't want to be trapped in the box, right? But I guess if I want to be RoboCop, then maybe that's where I'm headed. So they're using our compute to figure out how to engineer the proteins to actually be able to shoot pulses at them and control them, right? To figure out how to actually manipulate this neural tissue. Perfect. All right. We've got at McGill, Isabeau's team working on an approach called Hebbian learning. So the idea here is that instead of gradient descent, there's other ways to actually train your neural network. And Hebbian learning is the approach they're using. This is a better approximation of what the brain does. So instead of having a whole bunch of specific neural networks that are actually trying to do being trained to a particular job, you have these kind of sort of composable components that are sort of being arranged a bit more organically, and they're being trained in a different way. Maybe this will be the future, we're not sure. We want to help people who are trying new things, and maybe the transform architecture is not the last gasp for AI, even though it's been 7 years and we still don't have a new breakthrough. This one here is really interesting. This one's happening over at Berkeley. What they're doing is trying to figure out, can you do social science by asking LLM questions? And to do that effectively, you need to train a whole bunch of different LLMs to represent different populations. So you can ask them more questions and see how they might respond. So that's what they're up to on our platform. At Macquarie University in Australia, we're looking at better ways to actually pre-train vision transformers. So these are adaptations of BERT, the vision version of BERT. And the masked image examples here is where you go and take an image and you block out a piece of the image, and then you see if the neural network can fill in the bit that's been blocked out. We've done a few things ourselves as well internally. We're working with the Stanford AMI group, and we asked them what slows down medical imaging, right? And they said, look, you go get a CT scan, you go get an MRI scan, it's all going to output this file called a DICOM. It's like the PDF of the medical world. And this format has been around forever. It's been around for 20, 30 years. And all the tooling's there for it, but it was never developed with AI in mind. So when you try to use it in AI, it's extremely slow. And we adapted a few different open source projects, put them together into a format that's completely bidirectionally compatible with DICOM. It's open source as well. The cost is your files are going to take up about twice the space. The benefit is they're going to load potentially orders of magnitude faster for AI processing. All right, if you think any of that looks interesting and you would like $10,000 to $100,000 worth of compute to do something like that, then take a photo of this one and go and apply for one of our research grants. Everyone got that? Okay. As a more gentle introduction to our platform, we're running hackathons about every month. We've got one coming up this weekend. This is where you actually get to go live on a cluster. So if you're comfortable with PyTorch, maybe you don't have ad hoc access to a giant cluster of GPUs whenever you want, but you'd like to see what it's like to actually train on a cluster. You can come along here and we will give you a cluster. In fact, we'll give you lots of clusters. We did 1,100 GPUs at the last event. If you can use PyTorch, you can get up and running in about an hour on our platform, where you can now train on a cluster, and you get to watch a bunch your chess bot compete with a bunch of other chess bots. We also published the winning results. This was a great team that actually formed at the event, completely smashed the competition, and they were able to try a whole bunch of different approaches on the platform, and then go and iterate a couple dozen training runs, and they were able to do that all in the space of a weekend, because we're effectively your DevOps team. So if you'd like to take part in the chess event this weekend, that's the QR code for that. Bang.
This location.
Same location? Did it go to our website or to Luma?
You are
Sorry? If it went to our website, the top of our website has the link to the chess competition. Like it's in the headers. Sorry, we just started with the QR codes like 2 days ago.
Well, what if we do the better mic?
You want a better mic for me?
Yeah.
Cool, okay.
So now it's Tony Robbins style, right?
Tony Robbins stuff.
Yeah.
Hey, there we go.
Here we go.
All right. Developers.
I'm using that.
Okay. So now my favorite bit, right? The Dyson Sphere. So why do we want to go and build a Dyson Sphere? So if we can make AI that's actually doing something good, we're going to want to make a lot of this AI. And we're going to want to build it in a way that doesn't completely total our living space while we're doing it. So you've seen the energy demands going up for compute, and I think we can go and put it in a better place. All right. All right, so this is sort of the Dyson Sphere of science fiction, right? Some kind of shell, some kind of cluster of satellites or something around the sun. You might think this is really cool, or this is pointless, or this is crazy, but whatever it is, it's way out there. That's something for our far distant, descendants to even conceive of. But we can actually get started on this much sooner. All right, it's not a sci-fi fantasy. It is much cheaper energy. All right, the best power on Earth today, cost-wise, comes in at about 4 cents US a kilowatt hour. All right, obviously in California, if you're looking at your bill, it's maybe an order of magnitude higher than that, but the wholesale rates in places where either there's easy access, plentiful renewables like Iceland geothermal, wind in Texas, next to a giant hydro plant in Malaysia, that's kind of the cost that you're looking at. And that's where people want to build data centers. If we get up just a little bit into orbit, we can actually bring that cost down. But if we go into full Dyson Sphere mode, we can make energy so cheap, the vision of like nuclear fission, right? So cheap we won't need to meter it, right? We can do a huge amount. And we'll have a lot more. So if you think about how much, energy we have on Earth, if you look at how much the sun's just, fusing into space, there's a lot to go around.
What?
So this is that little blue bit up the top is how much we actually use each year of energy. All right? If we burned all the oil, all the gas, all the coal, right, used all the uranium, it still wouldn't add up. Put in all the wind and hydro and everything else that we could, it still would not add up to just the amount of sun that hits the Earth each year. But solar energy is really inconvenient because it's only available when the sun is shining. Now, the good thing about space is the sun is always shining. All right, so we don't have to worry about batteries anymore. So if we're going to build this Dyson Sphere, we've got to think about where to put it.
Sheep.
All right, so we've got the bits of sort of that you may be more familiar with, and then we've got these spots here. There's Lagrange 1 and Lagrange 2. That's where the Earth and the Sun's gravity kind of cancel each other out, so you can kind of just hover there in space. We've also got this little cool guy here. This is the Parker Solar Probe. Does anyone know about the Parker Solar Probe? Mm-hmm. Yes? Couple? All right. It's one of my favorite things because it's the closest we've ever got to the sun. So it's kind of like a proof of concept of how close we could build the Dyson Sphere to the sun. So where are these things, right? We're at 1 astronomical unit, or about 150 million Ks from the sun. Venus and Mercury are kind of spaced out evenly along the way. The Lagrange points, Earth, Moon, everything, they're all kind of pretty close to each other. Mars is a little bit further out. And the Parker Space Probe is really close to the sun, right? It can get to 0.04 AU, or like 96% of the way from the Earth to the sun. So it's pretty amazing that we can actually build something that can survive in those conditions. So let's have a look at how much energy we get, right? If we go stick a solar panel in Earth orbit, it's going to pick up a little over a kilowatt per square meter. and the space temperature is about 120 Celsius. Sorry, I'm from Australia, so I don't know what Fahrenheit is. All right. Now, if we go to Mars, which some people want to do, we get about half the energy, a little bit less than half the energy on our solar panels. A little cooler, although, we're fine at 120 in terms of space engineering. So how about if we go the other way? We go to Venus, we're going to double that energy. It's a little hotter to deal with. Conventional photovoltaics can kind of operate there, but they're starting to struggle. If we go to Mercury, where we're getting up around 5 or 6x now, and it's getting quite hot. So conventional photovoltaics are going to struggle. But thermophotovoltaics, which are, I think, underdeveloped, understudied relative to what we can do with photovoltaics, can really hit their strides in these sorts of environments. And they're able to capture a theoretical max of 85% of the solar that's hitting the sun energy that's hitting them. Currently, they're about 10%. Now, if we go all the way to where the Parker Space Probe is, what do we think that watts per meter squared is going to look like? Any guesses? Anyone?
10x, 100,000.
We've got 10x, we've got 100,000. It is, before we get there, I'll leave you hanging on that. So it's sitting in the sun's corona, which is 2 million Kelvin. Like, how on earth is anything surviving there? The reason is that while the corona is extremely hot, it's also very low density. So what it actually has to survive is 1300 Kelvin of heat versus 2 million Kelvin of temperature. All right, so we had some guesses of 10,000 and 100,000. All right, this is how much you get per square meter when you're this close to the sun. And this is because light diffuses as you get further away from the object. So we are looking at, a huge amount, right? Like 600 times more energy, right? The same solar panel sitting in Earth orbit is going to capture 600 times the energy if it is as close to the sun as we have built an object that can survive. And within the temperature range of what the solar panels, the thermovoltaics, can actually operate at as well. So we have technology today that is right now flying around the sun, can do this, but can also survive at those distances. All right, so that is the goal, right? Maybe we could even make it a little closer, but I think that's still pretty good, right? We're getting quite a lot of energy back. All right, so that's the win. All right, now there's a few folks who are already heading in this direction. Has anyone heard of Lumen Orbit? Yeah, all right, a couple. All right, so Lumen Orbit is a pretty recent company. They started this year. They've raised about $14 million. They want to build low Earth orbit clusters. This is where we're talking about the sort of the 1 cent a kilowatt hour kind of trade-off versus 4 cents a kilowatt hour. And they're going to be made financially sensible by Starship. So the best place for a data center, as soon as Starship is running, is going to be low Earth orbit. You will pay more money to run a data center on Earth than you will to run it in low Earth orbit. Right? But we can still get a lot more energy out of our panels if we get closer to the sun. And before we get there, I just wanted to show you one other company. So this is Astroforge. Has anyone heard of Astroforge? All right, so they're mining asteroids, right? They've raised about $50 million, and they are going to make it so even though Starship is so cheap to get stuff into space, we might even be able to capture a whole bunch of resources in space cheaply and practically with Astroforge, so we can take even less mass into orbit. The goal here is to get all infrastructure off the planet, right? The planet should be a place for people, plants, and animals, and everything else should be up in space, where there's far more plentiful energy, enormous amounts of resources, and the mess just doesn't matter. All right, so it's great that we can build around Earth with Lumen and Starship, but I want to get to where the Parker Space Probe is. And the problem of the Parker Space Probe is it took 7 years to get close to the sun, and it didn't even get into an orbit around the sun. Right? It got into this sort of elliptical orbit where it kind of goes around the sun and around Venus and everything, right? So that's not going to work. We need to be like in a tight orbit around the sun. Same distance, but just like keeping that constant. And so we need about 30 kilometers a second of delta V to do that. To get off the planet into low Earth orbit, we need about 8. So we built rockets that can do this. The problem is when the rockets get into space, they have used all that fuel, right? And so they can't really do much more after that. Like they were able to use a really big rocket to take the Parker probe into the LEO, but then they could only had room for a sort of small booster that could give it another 3 kilometers a second of delta V, the ones that actually got into LEO, which is why it took so long to get near the sun. But now that we've got Starship and we can just go and send rockets up and refuel them over and over again, we can kind of have an entire, launch infrastructure ready to go in LEO. So we could actually just head to the sun. Now it might take a few goes, right? We might need to send like a giant mass of starships towards the sun, and then they refuel, a fraction of them, and then they kind of boost on and keep going. But by my calculations, by which I mean like yesterday with me and ChatGPT, I think we could get there in a couple of months, right? But this is quite a lot to take to the sun. So I was doing some other research on other ways to get to the sun quickly, and I think the answer is railguns, right? I think we build a great big railgun that can shoot GPUs at the sun at 100 kilometers a second. I think that's the best thing we can do for AI. I'm really excited about this. So there's concerns around the practicalities of running data centers in space. I encourage you to go check out the Lumen Orbit white paper. All right, they've addressed a huge amount of this, and the pieces they have not addressed, I've spoken to them directly on this, and I'm pretty confident they've actually got solutions for them. So yes, you do get cosmic radiation in space. It will shoot things to bits. We have put hardware in space for a long time. We do have solutions to this. It's just a question of can we do that cheaply enough and in a small enough package that it doesn't ruin the economics here. All right, so with that, come grab a research grant. Come to one of our chess hackathons, and if you want to talk about Dyson Spheres or read more about my ramblings, this is where to do it. Just